And the talk will be about links between eddy horizontal and vertical structure, a geostrophic turbulence interpretation. So Elizabeth, please go ahead.
Yeah, thank you for the introduction. Yes, so I'll be speaking about the relationships between eddy horizontal and vertical structure and what existing geostrophic turbulence ideas can tell us about specifically the vertical structure of mesoscale eddies in the ocean. So I want to motivate this talk by basically kind of mentioning the fact that a lot of prior works and literature over the last several decades have asked the question of what sets horizontal eddy scale and also the horizontal eddy structure. This is partially due to the greater availability of horizontal information about mesoscale eddies, for example, stemming from the satellite era. But gaps remain in constraining the vertical structure, and that is the subject of this talk. So just want you to remember a few important length scales for the course of this talk. The first of these is the Rossby radius of deformation, which is the dominant length scale of baroclinic instability in stratified shear flows. And a map of this deformation scale is shown in this figure. You can see that it ranges from just a few kilometers at the high latitudes to a few hundred kilometers in the lower latitudes. Another important scale is the Rhines scale. So this governs the crossover between kind of vortex dynamics and waves and jet dynamics. And this is a function of a barotropic velocity and also beta, where beta is the change of Coriolis parameter with latitude. There's another version of the Rhines scale, which is the topographic Rhines scale. And in this case, beta is replaced by beta star, which is comprised of the standard df dy, but also has this term that stems from gradients in the topography. So for example, if you have a sloping bottom, that can also impose a PV gradient that can influence kind of jet versus vortex dynamics. So I'd like to point out that all of these are horizontal length scales, and these have been invoked in various ways to try to explain kind of the QG dynamics and really explain horizontal eddy structures. But I'll be trying to use these same horizontal length scales to infer something about eddy vertical structure. And another thing I should mention that I'll come back to later in my talk is that a really important application of both understanding the horizontal structure and the vertical structure of eddies is the eddy parametrization problem. So for example, in parametrizations that rely on the Jent-McWilliams scheme, there have been efforts to try to formulate a mixing length which is potentially related to some of these scales. And I'll also be speaking about how understanding the vertical structure can be really important beyond just the horizontal scale of the eddy. Okay, so I want to just, for some background information, show you this slide. The idea here is that we're going to decompose the flow into vertical modes. So these are the QG modes, assuming a flat bottom. The idea of this is if you have a velocity, you can write it as a sum of these orthogonal components. The first of these is the barotropic mode, which is uniform with depth. So you can think of this as just the vertically averaged component of the flow. And then we have progressively higher baroclinic modes. So for example, the first baroclinic mode has a large amplitude near the surface and then decays to something that's negative at depth. It has 1 zero crossing. And then the second baroclinic mode has 2 zero crossings, and kind of progressively with each higher mode, you have more zero crossings in the vertical. So a more complex vertical structure. So if we think about our flow in terms of these modes, we can also think about the energetics that arises from that. So this is a figure from Ferrari and Wunsch, 2009, but this same idea has been proposed by prior studies, such as Smith and Vallis, 2001. Basically, the idea is that you have these baroclinic modes, and the ocean is forced in kind of a variety of different modes. But within the baroclinic modes, we see an energy cascade to smaller scales. So this is the forward energy cascade. Then at the Rossby deformation scale, which I mentioned in the previous slide, we see a transfer of energy from the baroclinic modes into the barotropic mode, which is again the uniform with depth mode. And so as a result, once this energy gets transferred into the barotropic mode, because it's now a 2D flow, we see 2D turbulence behavior, which is that there is an inverse cascade of energy to larger scales. And here RE refers to the Eddy scale. So eddies are initially kind of developing at the deformation scale, but then growing to this RE. And at some point, their growth and this inverse cascade is arrested by some process. So this could be bottom dissipation, bottom drag, or it could be the formation of something like jets. And so the question is, how can we use some of these scaling ideas to infer something about the vertical structure? And here, when I refer to vertical structure, I'll be really referring to the partitioning between the barotropic and the baroclinic energy of the flow. So in the 1990s, Larachev and Held proposed that the scale separation between the deformation scale, where the eddies start to grow, and the energy containing scale, which is RE, is what governs the strength of the inverse cascade. And also this sets the barotropic to baroclinic EKE partitioning. So this really sets the vertical structure. Just to emphasize what I mean here, if we imagine that the deformation scale, for example, is at 10 kilometers, and then our eddies are growing to a scale of 20 kilometers, this situation is going to be less barotropic than a situation in which the eddies have grown to a larger scale. Of course, the question is then, like, what sets the eddy growth and what sets the arrest of this inverse cascade? So kind of what limits RE, but I'll be speaking about that later as well. Okay, so if we try to apply this Larachev and Held 1995 idea, we can actually quantify this better than I showed on the previous slide, which is that we can say that the ratio of the eddy scale to the deformation scale is going to be related to the ratio of the barotropic to baroclinic eddy kinetic energy. And apologies, there should be a square root there. So I actually tested this idea in an idealized model. So I computed the eddy scale using the sea surface height, which is, again, something that you can observe. It's a two-dimensional field from the surface. And the really interesting thing, if you look at the figure on the top right, this is kind of a zonally averaged view from this model. And I'm showing two metrics. One is that ratio of RE to RD in red, and one is the barotropic to baroclinic EKE, square root of that, in black. And so you can see that there's really remarkable agreement throughout most of the domain, with the exception of the southern region, which is the ACC. You can also see the same thing on this scatter plot. So the one-to-one line is in black, and we can really see that this relationship holds pretty well. And so again, this means that we can really infer the vertical structure just from knowing the sea surface height and the deformation scale. But of course, this is a really idealized model. And so then I wanted to ask, what about in the real ocean, or what about in a much more realistic and high resolution climate model? So then I started collaborating with Jacob Steinberg, and we basically looked at some observational data to get a better sense of what's going on in the real world. We looked at 4 locations that are shown in red dots on this map. Note that this map is showing bathymetric roughness, so just how jagged the topography is at a given location. And so you can look at these 4 locations. The Erminger Sea and the Argentine Basin are these 2 points. We can see that if we look at the time series of eddy kinetic energy as a function, so this is kinetic energy as a function of depth and as a function of time. We can really see that a lot of these eddy features have a pretty barotropic structure. And likewise for the Erminger Sea, whenever we see kind of an eddy feature passing through the mooring location, it's really extending throughout most of the water column, even if this water column is several thousand meters in depth. In contrast, the locations in the Southern Ocean and this location at Station Papa both have a much more baroclinic structure. You can really see that these eddy perturbations at this location are pretty surface confined. So this gives us some hints that the bathymetric roughness could be a really important factor, because again, the really smooth topography is where we see the highest barotropic values. And this is also consistent with the Larachev and Held idea, where the more we allow our flow to barotropize without inhibiting the energy cascade, the more barotropic the flow will be. So then we decided to move this analysis into a global climate model. So this is 1/10 of a degree resolution. And so what Jake did, he created this figure, and he basically took the smoothest topography class from this previous figure, and we overlaid this black ice line on top of the barotropic to baroclinic kinetic energy ratio. So the color just shows the barotropic to baroclinic kinetic energy ratio, and the black line shows where we have the smoothest topography. And you can really see here how in the really high barotropic regions where that value of barotropic to baroclinic kinetic energy is high, that is where we also have kind of the smoothest topography and very highly barotropic eddies. So then we wanted to investigate this in more detail. And so we applied the same data set. So this is this CM 2.6 model, 10th of a degree resolution, 50 vertical levels. And we performed some k-means clustering where we basically just took the velocity profiles at every point in the model. And we removed all the geographical information. So we concatenated all of these eddy velocity profiles into one large matrix, and then asked this algorithm to identify similar regions where the eddy vertical structure looks comparable. And again, there's no geographical information in this clustering. And what we see is actually that we do obtain some geographically coherent structures. In particular, I want to draw your attention to cluster 1, which is the highly barotropic cluster. You can see here in this figure, I'm showing the normalized standard deviation of the velocity as a function of depth. And you can see here that it's pretty uniform with depth. This is in contrast to something like cluster 3, for example, where we see a lot of baroclinic kind of surface confined structure, which is reminiscent of the equatorial region. But again, this is encouraging because in cluster 1, that is where in the observations, we also saw highly barotropic structures. And in the model, it seems like there's some agreement with that. But then the question is, how can we more precisely say what the barotropic to baroclinic partitioning should be in all of these regions? And so then I went back to some of the existing literature on turbulence. So for example, this is a study that I mentioned previously, but there have been a few other follow-ups kind of doing similar things. The idea is that there are these two broad regimes, one of which is F-plane dynamics. We see this in higher latitudes. So here the scale separation between, again, the Eddy scale and the deformation scale is what sets the vertical structure. We also have a beta plane regime, which is prevalent in low latitudes. And here it's the scale separation between the Rhines scale and the deformation scale, which is setting the vertical structure. And again, this is because the inverse turbulent cascade is arrested by the beta effect and the formation of jets. And so there are also this set of studies by Gaia and Ferrari from a couple of years ago that similarly examined these two regimes, and they kind of highlight Jupiter as an interesting example of this, where in the high latitudes where we have F-plane dynamics, we really see individual vortices. They call this a vortex gas. And then at the low latitudes where the inverse cascade is arrested through zonostrophy, it's really kind of jet-driven flows. And so I wanted to test this in the ocean and see whether or not some of the scaling relationships that exist for these two regimes can be applied. And so first, I just took this kind of sector in the Pacific Ocean that didn't have any boundaries and computed this parameter, which Gaia and Ferrari derived, which basically governs which regime we're in. So this is the ratio of the Eddy scale to the Rhines scale. And the idea is that when this parameter is larger than 1, then we have kind of a jet-driven dynamics, so beta plane dynamics. And then when this parameter is less than 1, it's more like vortex dynamics. And then I came up with this like really rough flow chart of how to think about the scaling relationship that applies in each of these regimes. So the first question is, are we near the equator? If yes, then we're in the zonostrophic regime, and then it's the Rhines scale divided by the deformation scale, which is the governing relationship determining the partitioning of energy in the vertical. If we're not near the equator, then we're in the vortex regime, and then the inverse cascade is arrested by bottom drag and bottom friction. So then the character of the bottom becomes very important. So if the bottom is smooth, then it's that same relationship that I showed earlier that worked in that idealized model, which is Eddy divided by deformation scale. And then if the bottom is not smooth, then it's the topographic Rhines scale that is important. And so I tested that, that approach, and basically this is showing the results from that. So on the top, I'm showing the scaling for the low latitudes. So this is the beta plane situation. And on the bottom, it's the F-plane case. So the scaling relationship here is the Rhine scale divided by the deformation scale. And on the y-axis, we have the barotropic to baroclinic partitioning. And then for the lower case, it's just the topographic Rhine scale. And the one-to-one line shows kind of the prediction. In both of these cases, we see really good agreement, particularly in cluster one, which is that highly barotropic purple case. So overall, kind of this confirms that these scaling relationships can really tell us a lot about eddy vertical structure. And I'm running out of time, but I just also want to mention an application of this work, which is the parametrization problem. So here, I'm showing basically the energy cycle of the ocean. We have potential and kinetic energy that's maintained by buoyancy forcing and wind stress. And these two reservoirs can interact with each other through the overturning circulation and also through mesoscale eddies. So eddies are known to extract potential energy and convert it to kinetic energy. Problem is, if we do not resolve eddies fully, then we have this unresolved eddy kinetic energy reservoir, which in theory should be interacting both with the potential and kinetic energy of the large scale flow. And so past parametrization approaches have tried to constrain some of these components, such as this Jen McWilliams piece, which removes potential energy from kind of coarse simulations. But one of the ideas that I've explored is basically incorporating vertical structure into how we parameterize the reinjection of energy that's driven by eddies. So this backscatter component, backscatter refers to basically energizing the flow in a way that's consistent with eddy dynamics. And there's been a lot of research recently about how to parameterize backscatter in the best way. But I've really been focusing on the vertical structure aspect of this. So if we look at the momentum equation, the backscatter term is just this Laplacian, which is, it's basically injecting energy in the same way that it would be dissipated, except it's an anti-viscosity instead of a viscosity. And so what we did here is that we prescribed a vertical structure for this nu2 coefficient. Okay, and just to show you what that actually does. So again, this is an idealized model that I mentioned earlier. So this is the high resolution version of it. So it has a 3-kilometer grid spacing. Then there's a coarser version, which is 0.5 degree, 50-kilometer roughly grid spacing. And then we have kind of the existing state-of-the-art scheme, which I showed on the previous slide, which is by Janssen et al. 2020. This does not have any vertical structure in it. So what we did, I should acknowledge my co-authors here, so Scott Bachman, Schaefer-Smith, and Laura Zana. What we did is that we imposed vertical structure onto the backscatter, and just for suspense, adding a drum roll here. And this is what it looks like with our parameterization with the vertical structure. So you can see that there's a pretty large improvement compared to both of these cases. And again, this is still a 0.5 degree model. So really kind of remarkable results and something that we're really excited about. And I should also note that one cool aspect of this is that even though we just focused on parameterizing the momentum fluxes and imposing the correct vertical structure onto those, in the process of doing so, we also significantly improved the buoyancy structure as well. So these plots on the left with the red lines are showing isopycnals for the case with no parameterization compared to the truth in black. And on the right is our parameterized case in blue, the truth in black again. You can see that in the case with no parameterization, we see overly steep isopycnals in numerous parts of the domain. That is, for the most part, significantly improved with our parameterization. Also, the outcroppings of certain isopycnals in the ACC are significantly improved. And yeah, the potential energy of this parameterized simulation is more in line with the truth. So I'm going to end here. I'll just leave up these results and happy to take some questions.
In this last slide, why didn't the state-of-the-art parameterization work? But also backscatter, right?
Sorry, can you say that again? I couldn't hear you clearly.
Your last slide, the great success. Why didn't the state-of-the-art backscatter parameterization didn't work?
Yeah, there were multiple things that were going on. So the first, so I think the main issue is that it did not have any vertical structure. So it was purely backscattering into whatever vertical structure the flow already has, which was just maintaining the overly baroclinic nature of the flow. But also it was unstable. So we implemented basically a technique that was meant to stabilize the backscatter as well. So that allowed us to increase the magnitude of it, but then also the really critical piece was having the correct vertical structure for it, because otherwise the energetics were not correct.
Wasn't the backscatter parameterization shown to be successful in some way or the other? I saw versions of it where it did work.
Yeah, I mean, it does work in terms of helping energize the flow a little bit and getting the potential energy correct. But let me just show you another slide here. Let me see, hold on. Yeah, 1 second. Okay, so here I'm basically using the previous version of that parameterization, so the one that you're asking about. And I'm showing kind of a parameter sweep that I did where I considered various backscatter and various GM values in this scheme. The first problem was that it was unstable, but then even if we get the potential energy correct, so if the ratio is 1, kind of in this starred area, the kinetic energy of that simulation is still like 20% of the truth. And so in some ways it works because it gets the buoyancy structure correct, but it does not energize the flow. It does not increase the kinetic energy enough to be close to the reference case. And also the vertical partitioning of energy in that simulation is not correct. So there are things it does, but there are also ways in which it could have been improved.
Yeah. So
Yeah, go ahead.
in the clustering, you did not include any geographical data. Is that not useful or not correlated to the vertical structure given?
Yeah, I think it would be useful, but I wanted to remove as many parameters as possible from the clustering algorithm. And I think it's kind of a more powerful result if these geographical patterns come out on their own without imposing any information about where that given profile was taken from. So I think if this hadn't worked, maybe I would have added additional information. But I think just the fact that the eddy velocities alone led to the emergence of these geographical patterns was a good result. So it wasn't necessary.
More questions? Okay, then we can thank Elizabeth again for joining us from the UK, right? At the moment. Yeah.
No, I'm actually in
you.
Colorado right now.
Oh, okay.
It's like 3
Sorry.
a.m.
Yeah, thank you very much for your talk. And we take a little break and then we start with a tutorial on visualization with Python.
Yeah, thank you very much.